All right, welcome to Transformations Review. I'll be your host. As we work through this one, we're going to talk about rigid motions, the actual rules for transformations, and then we'll wrap up by doing some questions and having some good times here. Okay, so the first thing to do, rigid motions. Remember, rigid motions, another word for this is we talked about isometry, which essentially just means that the figure you get is congruent. So it preserves distance between the points, which means the side lengths are going to be equal, okay? And it preserves angle measure. So the distance or congruent sides and the congruent angles. Now the rigid motions we're talking about here are reflections. Oh, and where did the G come from? I have no idea. Reflections, rotations, and translations. All right, let's talk about rotations. Now, a rotation around the origin, we'll do that first. You can remember you can do swap and up. So, for example, the point 2, -5, we're going to swap them. So the -5 is going to go first, then we're going to opt the first number. So it's going to turn into 5, 2. Okay. 180 degrees, we negate both. So it would just be -2 and then +5. And then when we do 270, it's actually op and then swap. So we opposite and then switch them. So it's going to be -5, -2. Right? So it's swap and op, negate both, op and swap. All right? Okay, let's talk about this first question. What happens if I rotate around a point that's not the origin, right? What if I rotate point A 90 degrees about point B? And really what we want to do here then is we want to pretend that we can redraw the axes. Now I linked a video here, okay? So feel free to check the video out if you want to. It goes through pretty good, nicely about this. So what if we redrew the axis? What if we created a fake y-axis right here, right? And we relabeled this as our new x-axis, okay? Now, in terms of reading the points normally, we're normally going back to the origin, okay? But what we're going to do is we're going to pretend like this is my y and my x. So now point A, right? We'll just call it, we're not even going to call it point A. Call it whatever you want. This point we're talking about is actually the point 1, 2. Has coordinates, the new coordinates, right? The fake coordinates are the points 1, 2. And so if I take this point and I do a 90-degree rotation, I swap and op it, right? It's going to become -2, 1. All right? So from this axis, I'm going to go -2, 1, and I'm going to plot my point. And this point has now rotated 90 degrees about point B, okay? Now, that's it. We've now rotated it. So what we need to do to answer the question is, right, forget about my fake x and y axes and go back to the real one. And so this point is just point 0, 2. So A prime now has the coordinates 0, 2. And that's how you rotate 90 degrees about a point, or 180, or 270. You just create new axes, fake ones, right? You pretend like these are my new coordinates. I do my swap and op and swap, negate both, whatever it is, and then I graph that point using my fake axes, and then I read the point using the real axes, and we're done. Okay? Rotational symmetry. Now the order is the number of times you can map a figure onto itself as you rotate 360 degrees. So if I turn this thing, right, you would say, all right, look at the points right up top. So boom, it's 1, 2, 3, right, 4, and then we're back to 5. So it's 5 turns that I can make going around. So the order is 5. So to figure out the angle of rotation, we just take 360 and divide it by the number of times that we can rotate it, that order. So in this case, 360 divided by 5, right, is going to equal, and it should be 72. And it's 72 degrees, okay? Now, some questions will say, which of these is the minimum number of degrees? And sometimes it'll say just which of these is a possible angle. So if it's possible angle, all I want to do is basically take 72, right? And then I'm going to multiply it times 2. And I'm going to get, well, it's 144. Or what happens if I add another 72 one, right? And and then another, and then another. And you get the idea here, right? You can just keep adding 72 on until you get like the number you're looking for. So 72 would be the smallest number of degrees that I could rotate. Other possible rotations would be 144, 216, 288, or 360. Okay, even 420 after that, but that's it. Okay, reflections. So the rules for reflections are, if you reflect on the y-axis, you just negate the x-coordinate. The point 2, -5 is going to become the point -2, -5. And the x-axis, I negate the y-coordinate. So this is going to be +2 and +5 if I change the y-coordinate. In y equals x, we just switch them, right? So this is going to be -5, 2. In y equals -x, we switch and we change the sign, we negate it. So that's going to be 5, -2. And if we do in the origin, it's the same thing as if we did a rotation of 180 degrees, right? We just switch the signs. That's it. And so this would be -2, +5. Okay? Now, what happens if it's not one of these y-axis, x-axis, y equals x, y equals -x in the origin? What if I reflect over a line? And so usually what happens is they give you a vertical or horizontal line. So in this case, if x is equal to 1, which is this line right here, okay, what happens if I reflect over that line? So all I'm going to do is count distance from point B to that line and then move past the same distance. So it's 1 here, 1 past, and this is where point B prime is going to go. Here it's 1, 2, 3, 4. I go 4 past, boom, and that's where A prime is going to go. And that's it. That's the reflection. Okay? Be careful when you're doing these questions that you read. Does it want you just to graph it and label it? Does it want you to, I even forgot there's a C here, right? 1 unit away. Look at that. Or does it want you to actually state the coordinates? Because that's another one. So make sure you're careful with the reading. All right. Translation. Remember, you're just adding. So you're just taking the points, you're taking the two numbers here, and you're adding it on to x and y. So the point 2, -5, with a translation of -3, 10 is going to be the -2 plus -3, or 2 plus -3, which is -1, and -5 plus 10, which is +5. Okay? Also, be careful. When they do the reflections, and especially the rotations, they also have to, you've got to make sure you identify the center. We'll get to that a little bit later. So a transformation that is not a rigid motion, if you remember, is a dilation. Okay? Because side lengths, right, distances, is not always preserved. It can be if the dilation is 1 or -1. But if it's anything else, it's going to get bigger or smaller. Okay, so a dilation about the origin. Remember, they're going to give you the center and then what the scale factor is, okay? And all you're going to do is multiply that scale factor times x and y. So if we do a dilation about the origin, let's say we do -2, 5, and let's say we do a dilation of -2 center at the origin, and the scale factor is -2. So all I'm going to do is multiply -2 times 2, which is going to give me -4, and then -5 times -2, which is +10. Also remember, if you're identifying the R value, you can just divide the image by the pre-image, and that ratio, whatever that is going to be the scale factor you're multiplying by. Okay? Let's do a couple questions here. So line A prime, B prime is endpoint, therefore -2. And 1614 is the image of AB after dilation of what half? Center about the origin. What is the length of AB? So a couple options here, right? If I do a dilation of 2 at the origin, these points are just going to get half as big. So I know that, right? For instance, this is a good one. A prime, B prime already has coordinates that are reduced, right? It wants to know the image of AB after a dilation of 1/2 center of the origin. Okay? Yeah, we're good. So if you took the distance between these 2 points, right? The distance between the 2 points. A couple options. We'll go through the first one. So we're going to go through 16 minus 4 squared plus 14 minus negative 2, which is really plus 2 squared. So this is going to be 12 squared, and this is going to be 16 squared. And you can just do that right on your calculator. So control square root, 12 squared plus 16 squared, and we get 20. Now remember, this is the distance of this line, all right? It is the image of AB after a dilation of 1/2. So these points have already been shrunk, right? So what we need to do is we need to enlarge them to figure out what B is. So once we know the distance between A prime, B prime, we just need to double that to get the length of AB. Your other option is if this endpoint of A prime was after a dilation of 1/2, I can double that and get the new point, and then I can just recalculate the distance. So this would be 32 and 28. All right? Okay. Let's talk about identifying the dilation. So here we have PQR, P prime, Q prime, R prime, dilation centered at the origin, determine the constant dilation. So remember, the image over the pre-image, okay? So R is equal to the image over the pre-image. All right, here we can just count. This is 1, 2, 3. 1, 2, 3, 4, 5, 6. So if we do image, which is 6, over the pre-image, that gives me a scale factor of 2. That's the constant of dilation. Okay? Now, what effect the constant of dilation has on proving the triangles are similar? We can just say here that the side lengths are proportional, right? Therefore, we can say that they're going to be similar by side, 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 or we can say that the angle measures are going to be congruent, all right? Which means this is true by angle, angle. So the angle measures stay the same. So it's up to you, but those are the two options. All right, grid below of triangle ABC, DEF, A prime, B prime, C prime is the image after a rotation around point A. Determine and state the location of B prime is if the location of C prime is 8, negative 3. So C prime is actually 1, 2, 3, 6, 7, 8. That's my point. Now what they said was that the center of rotation around point A. So remember, we want to make this our fake X and Y axes, okay? And so you can see that this point, 1, 2, 3, 4, 5, 6, right, had the coordinates of negative 0, negative 6, and then became the coordinates 1, 2, 3, 4, 5, 6, 6, 0. So what happened? They did a swapping up, right? They rotated 90 degrees. That's all that was, okay? So if we follow the same rule, okay, for point B, right, what's going to happen to it? That's all we want to know. And so point B, under the fake, right, fake axis has coordinates of 1, 2, 3, 4, and then 1, 2, 3, 4, 5. This is for negative 5. So if we do a swap and op, right, this should be 5, 4. And so if I go 1, 2, 3, 4, 5, 1, 2, 3, 4, that's where point B is going to go. All right. So now by reading it off the regular graph, this is 1, 2, 3, 4, 5, 6, 7, 1. So we would say B prime has the coordinates 7, 1. This is what my triangle is going to look like. Okay. So that's the first part. Are the triangles going to be congruent? And yes, we can say yes. A rotation is a rigid motion, if you want to say that. M-O-T, there you go. So all sides will be congruent. And triangles are congruent by side, side, side. All right. In the next one, image after dilation. Remember, the dilation tells us that we have like these two triangles are also similar, okay? The vertices are 0, 0, 3, 0, and it gives us these lovely vertices. The ratio of the lengths of BE to CD, so those ratios are the same as the ratios of any two other sides. So if we're doing BE to CD, and E, by the way, is right here, that's BE. So it's small to big, right? So let's just do what's the ratio of AE, right, to AD, and that ratio is going to be the same thing. And here you can count 1, 2, 3, 4, and this is 6. So if we just do 4 over 6, that's going to be 2/3, and that's going to be my answer. Okay? Here you can count the same thing, right? 1, 2, 3. This is actually 4.5. That's 4.5. And so you can see that if you do 3 over 4.5, it actually is the same thing, right? 2/3. Okay? And that's it. That's it for the first 2 pages. I'll send the second 2 pages out in another video. And have yourselves a great day.